Okay, so we're going to look at connected particles. This time, pulleys on tables. So previously we looked at a pulley where there were two things hanging, like either side. This time it's going to be on a table. Now the best way for me to describe this is actually just to start reading what the question says, and then we'll draw a diagram and it will help you to imagine what's happening here. But the best way is just to read it and see if we can think about what's going on. So two particles, A and B, of masses 0.4 kilograms and 0.8 kilograms respectively, are connected by a light, inextensible string. Particle A lies on a rough horizontal table. So I'm actually going to start off by drawing this table for a second. Here is my rough horizontal table, and it says that particle A lies on the table. It's 4.5 meters away from a small smooth pulley which is fixed at the edge of the table. So here's the pulley this time that is now at the edge of the table like this. And it says that the string passes over the pulley and B hangs freely with the string taut, meaning the string is tight, 0.5 meters above horizontal ground. Okay, so my diagram is not going to be perfectly to scale here, but it's saying that particle A is connected by a string, and then there is a particle B here, which is hanging freely. So the fact it's hanging freely means that it's not touching this other side of the table here, okay? It's just hanging in the air, so there won't be any reaction force between these things that we've got. And I guess I should also indicate a bits of the other information they've said. They've told me some distances. They've told me that this distance here is 4.5 meters. And they've also told me that this distance here is 0.5 meters. So it's kind of like imagining, if I was to show you an example of what this might look like, kind of on a table, I guess you can kind of imagine it. It's like something hanging over the edge of the table, like my keys on my lanyard like this. And so as my hand moves across, the keys like move down. Okay, so it's kind of like this at the edge of a table, that either it's most likely to be that when you release something, my hand is like particle A and my keys are like particle B. If I release, it's just going to start sliding down like that until one of the things hits the floor, or until particle A, which is my fist here, until it hits the pulley, which is my finger. Okay, so it's, instead of it being like this kind of scenario where things were going up and down, we've now got one thing going left and right and one thing going up and down instead. Right, so let's add on some of the forces. We need to say some of the different forces on the diagrams here. Let's talk about particle A for a second. Ishak, can you tell me any of the forces that are acting on particle A? So good, you've got 0.4 g, which is its weight that we've got here. Any other forces that we've got here, red one? Any other forces that we know must be acting on A?
This is the frictional force.
Good, so we've just read ahead a bit there, good. The frictional force of magnitude 0.08 g opposes the motion. So which direction do you think the friction will be going in? Yeah, good. It's moving that way, and so it's going to be going in the opposite direction, which is 0.08 g. Still a couple of other forces I think that we need to add in there. Tension, good. Which direction is the tension? To the right, because if you imagine being that particle, you would feel like the string was bringing you forwards. There's just one more force we've not put in. The reaction force. There's going to be a normal reaction force, because it's actually sat on a table. You know the ones that we had hanging on strings? They didn't have a reaction force. Why didn't they have a reaction force? They were in the air. They're not touching anything. So there won't be a reaction force unless there's actually a contact. Sometimes that normal reaction is called the contact force. In other words, it's got to be touching something, okay? So those forces are all completed there. Now let's think about these forces that we've got here. These forces, well, I think the mass of it is 0.8 g, so I can, 0.8, so I can say the weight is 0.8 g. And the tension is going to be going up, because again, if you imagine being that particle, it would feel like the string was pulling you vertically upwards. So hopefully what we're recognizing here is, although this has a different setup, this is going to be identical in many ways to what we've just been doing on the previous example with the pulley and something vertically hanging over the pulley. The system is released from rest. It's often going to be from rest, okay? But just it's worth noting that when we do any suvat later on, we're going to have that process. So the things it wants us to do is it wants us to find the acceleration and the tension. And I've put those in orange because that's the same thing that we've had in our checklist before of just doing equation of motion, and then simultaneous equations. So there's nothing different there. And then part C is a little bit of an easy part of suvat, just finding out how long it takes to reach the ground. And then part D is the bit that I've put in purple because it's the thing that's going to include that quite like long process of trying to work out what's actually happening in this question for that last part. The total distance travelled by A before it comes to rest. So let's start off by doing the parts that are in orange. So we're going to do the acceleration and the tension. What would you start off for this thing? What would be like the first thing you might do here? Nabil, what might you do for this one to try and find out acceleration and tension?
Could you suvat?
Probably wouldn't be able to do suvat on this one to find out the acceleration and the tension yet. There's something else we'd need to do first. Red one?
Do F equals ma for both of them.
Yeah, we're going to do F equals ma for both of them. We're going to find an equation of motion for both of them. Now that one was A. I probably should have labelled that this one down here was B. Okay, so we're going to do... I'll start off by doing the one for A, okay? So I'll have a look at A, and I'll be resolving it to the right, because I think this one is going to be moving to the right, and this one is going to be pulling it downwards, like this. So I'll resolve it to the right, and I'll do F equals ma. What is my F equals ma for this one here? T minus 0.08 g equals the mass, which is not 0.08, the mass is now 0.4, which is equal to 0.4 a. Now I'm going to do the same thing for particle B, apart from I'm going to be resolving it which way, up or down? Down, because it's moving down, and that's F equals ma. And so you get 0.8 g minus T equals its mass, which is 0.8 a. Very familiar, okay? We've got this really, really similar setup here. Just before we move on, this one is on a rough table. If it wasn't on a rough table, if it's on a smooth table, then that equation of motion would be really simple. It would have just been T equals 0.4a, because there would have been no frictional force there. So some of the questions you do in a minute, there might not be a force here, and that's perfectly fine for there not to be a force there. It's just because it's on a rough table in our example. So let's keep going. We've got equation 1 and we've got equation 2. We know that the trick is to take equation 1 and to add it to equation 2 because the t's will cancel out. So we end up with 0.8 g from this one minus 0.08 g from this one equals 1.2 a. So we'll do 0.8 minus 0.08 and divide it by 1.2. So it looks like we get the acceleration is 3/5 g. So I did 0.8 minus 0.08, and I divided it by 1.2, and I came up with 3/5 or 0.6. In fact, I'm probably going to use it as 0.6 g. It's probably going to be a little bit easier. I don't know really, we'll see. Same process as before. I'm going to use equation 1 to find out what the tension is. So for equation 1, gives me that T equals 0.4a plus 0.08 g. So that's 0.4 times 0.6 g plus 0.08 g. So that's 0.24 g plus 0.08 g. 0.24 plus 0.08, slow brain today, which is 0.32 g, or if we multiply that by 9.8, 3.14 newtons, and I've rounded that to 3 significant figures. Hopefully now we've done so many of these and so many of the hard bits, this now feels like one of the easier bits of the question. So this was part A, and down here this was part B to find the tension in the string. Okay. Should I just give you a few seconds to finish writing some of that out? So we know this is the hardest part of the question. This is the part that's probably still another 7 or 8 marks, even though we've done the first A and B. We know this is now the big chunk of the question. If this came up in the exam paper, it's usually the last question in the exam because it's considered one of the hardest bits. So all it wants us to do is it wants us to find the time taken for B to reach the ground. So we're thinking about how long B is going to take to reach the ground here. What kind of thing do you think this is going to be? Suvat, exactly. It's got to be Suvat. So we know the distance it's travelling. If we look at doing this one for B going to the ground, and we're going to take downwards as our positive direction. It just seems to make sense to take downwards as a positive direction because everything is going downwards. Looks like the distance it's moving is 0.5. What's its acceleration? 0.6 g that we got from over here because we knew that's what its acceleration was. And we know that it started from rest. And we want to find out what the time is for it to reach the ground. So we know that S equals ut plus a half at squared. So 0.5 equals, well, that disappears. You just get a half of a, which is 0.3 g t squared. So by solving that equation, if we do 0.5 divided by 0.3 g, and if we square root the answer, we get that t is equal to 5 root 3 over 21, which is 0.412 to 3 significant figures. And I'll just pause us there for a second so that you can make sure you've understood all of that and that you've written it all down. So let's go quickly through our little checklist that we've got down the side here. We've done the beginning bit that was in orange, which was F equals ma, F equals ma, and then we solved the simultaneous equations. We actually don't feel like we've done any of these things yet. We've just answered part C, which was to find how long it takes for it to hit the floor. Let's try and imagine what's now going to happen afterwards, right? They're moving like this. This one's moving across and this one's moving down. We've found out how long it takes for this one to reach the ground. And we want to find out the total distance travelled by A before it first comes to rest. So A is going to be tugged along by B hitting the floor. After A has travelled 0.5 metres though, what's going to happen? The tension is going to go, because once B has hit the floor, that string is going to go all kind of wobbly because it's no longer going to have any tension in it. So if the tension has gone, what else is going to change about A? The acceleration of A will change because A was only accelerating here because there was tension. If there was no tension, if I were to get rid of that, the acceleration of it's going to change. And in fact, can we be more specific? What's going to happen after B hits the floor and A is travelling along that table? It's going to decelerate, which means it's going to slow down. The reason it's going to slow down is because there is friction that is trying to make it slow down. So afterwards, it's going to travel for 0.5 meters speeding up, and then it's going to start slowing down because it has deceleration, and then it's going to come to a stop because it's decelerating, and that is what I'm trying to work out. When it gets to this point over here, when it has fully stopped, how far has it traveled in that time, in that space that we've got there? And I'm imagining the distance that we work out is going to be 4.5 meters or less. Because if it was more than 4.5 meters, particle A will have crashed into the pulley. So let's actually get on with the question. We know that there's always got to be a V becoming a U. So I think I need to find out how fast this one was traveling when it hit the floor, or how fast this one was traveling when it had gone 0.5 meters. But they're the same thing. So it doesn't really matter, okay? I need to do that bit to find out what V is in order to find out what U is in the new one. So let's actually find out what V is for this information that we've got up here. I'll do that in a different color to make it clear. So I want to now actually find out what is V. It's either B going to the ground or it's A moving right for 0.5 meters before the tension becomes 0. So I'm going to use these 4 that I've got up here, and connecting them together is V squared equals U squared plus 2AS. So V squared equals, well, that's 0. So we have 2 times 0.6g times 0.5. So V squared is 0.6g, and V is the square root of 0.6g. This is us now moving on to part D of the question. So, it's doing this loads today, the board. So B hits the floor, which means the tension becomes 0. If you're not sure what I mean by that, if you think about like the example with my keys here, when they hit the floor, you can see how well, if it hits the floor properly, you can see how the string all becomes completely loose, so there's no tension in the string at all. That's why the tension is becoming 0. Okay, if the tension becomes 0, we know that there's going to be a new acceleration, and we're talking about A. So A has a new value for the acceleration. What's the best way of finding out that value? Because in the previous one, it just always happened to be minus 9.8. How do you think I can find out what the acceleration is for A? Good, the equation we've got up here, right? This is the equation that we've got up here. So I'm going to steal this equation, and I'm going to take it down here, and I'm just going to say that t is equal to 0 now. Previously, we always ended up that the acceleration was minus 9.8, but it's not going to be like that here, because it's not free fall, it's on a table. So I'm going to take this equation, and I'm going to replace t with 0. So I get minus 0.08g equals 0.4a. So I'll divide both sides by 0.4. And so we get that minus a fifth g, or let's put it as decimals to just make this easier. We get minus 0.2g is the acceleration. Deceleration, really, isn't it? It's slowing down. And so we're really nearly there. We're going to do the last part of the journey. So we're going to do A traveling after B hits the floor. Well, we know that the acceleration is minus 0.2g. We're talking about this journey here, right? We're talking about after it's hit the floor, we're talking about this journey from here to here. The acceleration is minus 0.2g. What other values do you think we know about? Mabel, are there any other values we know for this last bit of Suvat here? Do we know what its initial speed is?
Yes, the last speed.
Good, it's the previous one's v. So the previous v has now become this one's u, which is 0.6g. Who thinks they know what any of the other values are? And I don't want it to be Ishraq, because Ishraq's doing all the hard work here, and you're going to start relying on him to always give answers. What about v? Does anyone think they know what the value of v might be for this? Pardon? It's 0. Why? Good, it comes to rest. And what was the thing I'm actually interested in for this whole question? The distance. So I want to find out what on earth is s equal to. Now, connecting these things together, we know that v squared is u squared plus 2as. So you get 0 equals, u squared is just going to be 0.6g. And we've got 2 times minus 0.2g times S. So multiplying this all out, we get 0 equals 0.6g minus 0.4gs. So putting it onto the other side, 0.4gs equals 0.6g. We can cancel the g's. So good job we kept the g's in there. And so S is equal to 0.6 divided by 0.4, which is 1.5. So we've done the suvat that made v become u. We found the new acceleration that t was equal to 0. We've done a bit of suvat. But now we have to do the very final thing, which is to solve the problem. Let's have a quick look. What did the thing even want us to find out? It wants us to find out the total distance travelled by A before it first comes to rest. So we knew when it got to this stage here, that was when B hit the floor. It had travelled 0.5 metres. And then this second stage of suvat, we said that it travelled 1.5 metres that we just calculated. So the total distance it travels is 2 metres. And by keeping everything in G and keeping everything as accurate as possible all the way throughout, like keeping things like this, we've come up with the very exact answer at the end, that the total distance is equal to the initial 0.5 metres that it did, plus the extra 1.5 metres. So the answer is 2 metres. I'm hoping that by having done some of this last lesson and then me set you some homework on those other ones, I'm hoping this one doesn't feel as overwhelming as the last time that we looked at this, and that we've taken it at quite a nice pace here. So what you're going to have a look for me is at questions 4 and 5 from exercise 10F. We're going to do that probably until about for 20 minutes. We probably will only maybe get one of those done in that time. I think it's one that's going to be good for us to try on the whiteboard together, and then we'll be finished with mechanics. Okay?